So if you look at the Pearson coefficient, it's normalized. It divides by absolute by averages and things like that. And if we look at this formula here, we subtract the mean rating here and just look at the differences. And that says, well, if Alice is somebody who always gives low rankings to items because she's not a very positive person, or else maybe Alice is a super optimistic person who always never rates anything below 3. Well, we take that out by taking out the mean. And then we take out how violently Alice sort of oscillates in her feelings by dividing by this these sums of the squares of the ratings minus the average rating. So these are all designed to normalize out difference in different sort of trivial differences, because nobody really knows if you have a scale from 1 to 5 or 1 to 7. Quite how you normalize in that scale is not so obvious. And so if you do that, you'll find that the two which so here we have Alice, which is blue. We have user 1, who's actually this green one, who's actually pretty similar to Alice in shape, and so has a good similarity near Alice. Just happens to be more negative than Alice, so user 1 just has everything lowered. And user 4 is dramatically different from Alice, totally different shape. And we saw that with a minus 0.79 similarity between user 4 and Alice. And there are other measures, but this is meant to give the best results from empirical, maybe A/B testing or something. You would decide which type of method to use from the A/B testing strategy we described for Netflix in the first unit of this section. So now we've decided who's near Alice, and we should say only actually sum here over the users whose similarity is high. We certainly don't want to sum over negative similarities. That would give sort of all sorts of funny answers. So we're implicitly only summing over the case where sim is high and certainly positive. And then we just sum over, here we have a user A who is going to be Alice. We have an item P, which is going to be item 5. We take the mean rating over rated items for Alice, and we add on this weighted sum here. We weight it by the similarities of the ones that are most similar to Alice, get the highest weight, and we just put in the rating for this person, for this item, minus the average rating. In the same spirit as before, we're trying to normalize everything and take out the averages. So this is the prediction for Alice's ranking of item 5. And this makes a lot of sense in my opinion. And so here this summarizes this method. You take a user, you find the k nearest neighbors based on this similarity, and k is fixed by experience. You have an intuition as to what the right value of k is. You don't vary k within the job. And then you look at all the items rated, and where purchasing is sort of a yes-no rating by these nearest users. You remove all the items of which Alice is, you've got this, you don't have all the items because you're only looking at the items from the nearest users, because those are the ones we're going to be predicting. We're not going to predict anything which the users which aren't near Alice have actually purchased. So we've already got down to a pretty small number of items at this stage. And we remove the items already purchased by Alice, and then we take all the remaining items, use that formula we had on the previous slide, and we have various heuristics on choosing which users to include, and there are lots of papers in this area. And then we just return the top ranked items. So that's user-based collaborative filtering. And there's also, remember, this is not a theory, so there's no exact answer. And remember, we have the A/B testing to test any old idea. So we can use all sorts of heuristics and intuitive ways of modifying that. And controversial items might require more weight, because maybe agreeing on those is a more interesting thing to do than agreeing on the commonly liked items. This is this long tail idea. Um, so when the number of items which are rated in common by the different users is small, you may wish to just reduce, not consider that so seriously. And then you take when this, you don't necessarily use similarity as the measure. In fact, when the similarity is very close to one, maybe you make a similarity of one more, I mean, which gets weight one in that formula, and then you actually weight it more than the say the thing which has 0.9, which is pretty similar um, similarity. So the trouble with that similarity is it doesn't weight the very close things well. I mean, a trivial thing to do is you could take that similarity and raise it to the fourth power. 0.9 to the fourth power is around, I don't know what it is, 0.7 or something, or 0.6 something, and 0.68 or something. And if you just weighted in that, take that formula and replace similarity by similarity to the fourth power, you're going to give higher weighting to those similarities near one. And as we discussed, we can use a threshold and similarity only include all users with similarity greater than or equal to 0.85 or something, or you can use a fixed number of neighbors. Take the neighbors with the top similarity and include, say, at most 33 of them or something. So these are all intuitive things, heuristic things, which are used to make this better. And unless it's very difficult to decide what the right thing to do is, unless you either are really active in the research or you actually are in Netflix, Amazon, ... And all, I mean, obviously this is very important commercially. These are proprietary secrets. And so very little is actually known for real as to what the winning ideas are. So we now go on to a more general discussion of something we've alluded to already, the importance of vector spaces in formulating these things mathematically so that the concept of distance, etc., can be brought to bear to give you good intuition as to what's going on.